Hello, everybody. My name is Adam Herrmann, and I'm here to talk to you today about some work we've been doing in the AVS laboratory on autonomous spacecraft tasking using Monte Carlo research methods. So a quick overview of the presentation. We're going to go through the motivation, problem formulation, methods, results, and conclusion. On to the motivation. So spacecraft operational autonomy offers several benefits, including reduced planning latency, reduced operational costs, and more responsiveness to unexpected science opportunities. However, several challenges still need to be overcome. Onboard computational resources are very limited. Verification and validation needs to be performed so that we know these agents are safe in orbit. And without sacrificing those first two things, we need to know that these solutions are either optimal or near optimal to leverage the full capabilities of the spacecraft. So in this work, we focus specifically on the Earth-observing satellite scheduling problem, where one or more Earth-observing satellites must collect and downlink data to one or more ground stations. There are many variants in literature. Here we focus on a single spacecraft, multi-ground station, and area data types where the imager simply needs to just point at the ground and collect data. Past solutions include rule-based agents that are fairly simple in ability. And literature, it's very prevalent to use optimization-based techniques like mixed integer programming, simulated annealing, genetic algorithms. But these are very computationally expensive, and they typically don't generalize well to initial conditions that haven't been solved for yet. So in the last 5 years or so, a specific domain of algorithms or class of algorithms has been shown to be useful for spacecraft problems. Specifically operations or GNC problems. So some good examples include shielded proximal policy optimization applied to the OS scheduling problem. That was done here in the AVS laboratory. Also adaptive guidance for landing scenarios using recurrent neural networks. JPL's applied the reinforce algorithm to small body mapping. And there's been some work at Stanford looking at stochastic motion planning for hopping rovers on small bodies. So lots of work in this area, and these algorithms have shown to be very useful for spacecraft planning problems. This research focuses on a class of techniques known as Monte Carlo tree search methods. And the specific method used is the upper confidence bound for trees. It's an online algorithm, meaning that it simulates interactions with the environment to explore reachable states only. And it's nice because it only requires a black box simulator. It doesn't require a full transition function to be defined. And another nice property is that it converges to the optimal action as the number of simulations approaches infinity. AlphaGo is a class of techniques that AlphaGo is an algorithm that augments MCTS with value and policy networks to handle large action spaces. And in 2016, AlphaGo actually defeated a professional Go player, Lee Sedol, in a 5-game match. So our problem statement, we're going to develop a generalized planning solution for the Earth observing scheduling problem using MCTS and state action value function neural network regression. And by generalized, I mean that the solution is generalized over a variety of orbits or low Earth orbits and initial conditions. So now onto the problem formulation. We construct a basilisk simulation. It's an Earth observing mission in a 500-kilometer orbit with attitude control, power, and data management systems. And we're operating in a 3-orbit planning horizon. And the nice thing about Basilisk is that it's an open source simulation architecture. It's quite modular, and it's also very fast because under the hood it runs on C++. But you do all of the coding and interfacing with Basilisk at the Python level. So it blends itself very well to something like a GIM environment. So we actually take GIM, which was developed by OpenAI, and we wrap Basilisk in a GIM environment. And this gives a decision-making agent a standard interface to pass actions to and receive rewards and observations, both to learn from and to act on. And so we take a mode-based planning approach where we have high-level actions that are decomposed into low-level behavior for each mode. And every action is about is exactly 6 minutes of simulation time in that given mode. So we formulate the problem as a Markov decision process, a deterministic and finite horizon Markov decision process. And included in the state space are the inertial position and velocity vectors expressed in a planet-centered, planet-fixed frame. We also have several states for the attitude control system, like the attitude error in MRPs, the body rates, and the wheel speeds. And then we have several states that deal with resource constraints, like the percent charge in the battery or the percent fill of the data buffer. Our action space includes 4 modes: observation, downlink, charge, and desaturation. And as I mentioned earlier, our transition function is created using Basilisk. Our reward function in general is the amount of data downlinked in megabytes over a planning interval. However, if a resource constraint violation occurs, the agent or the environment returns -1,000 reward and the episode terminates. And a failure happens if either the battery goes to 0 charge or something like the data buffer is overflowed with data. We also use a discount factor of 1 because this is a finite horizon problem, so we don't really need the convergence properties offered by discount factors less than 1. So on to methods. Really, what we're concerned with doing in this work is solving for the optimal policy. And we solve for the optimal policy by solving for the optimal state action value function, Q star of SA. And that's just a measure of the kind of the expected value of all future reward given a current state in action. And so we do this with 2 methods. We do this with Monte Carlo tree search, and then we take the data that we generate with Monte Carlo tree search and we regress over it with state action value networks to generalize the behavior. So now I'm going to talk a little bit about how Monte Carlo tree search works. So at each step through the environment, MCTS uses a function called select action to run a predetermined number of simulations in a simulated environment to determine what the best action is. And so this select action function follows this basic process here, where it's repeated, X number of time, known as the number of simulations per step. So first, the agent selects an action based on the intermediate state action value function and some exploration bonus. If the agent reaches a state it's never reached before, it expands that node into each action and initializes Q and N. If it hits a state that it has reached before, the selection process just continues again until the end of the horizon. After expansion, the agent enters the rollout phase where actions are either randomly executed or some heuristic policy is followed to the end of the planning interval or horizon. And then after rollout, the realized reward is backed up through the search tree to update the intermediate state action value function. We also do some post-processing. We also do some post-processing on the data to assemble it for training. So after each completed planning horizon, we take the search tree and we back up the reward found throughout the search tree along the main trajectory to get a better measure of what the state action value function is along the main node. And we keep the other 3 nodes at each level of the search tree at the intermediate state action value function. So in this work, what we're interested in doing is generalizing behavior. So we run a large number of Monte Carlo tree search episodes on a large number of different initial conditions to generate training data. Here we use 1,200 different initial conditions. And then we pass on this data to train a value network. We validate the value network by executing it on a test set of initial conditions, and then we get the performance metrics out. So now I'm going to talk about some of the results and the hyperparameter searches we conducted for both MCTS and the value net. So for a hyperparameter search for Monte Carlo tree search, we looked at 3 different things. We looked at the exploration constant C, and this just balances the exploration versus exploitation problem that the agent faces. So it offsets the known value for each action with an exploration bonus. So C is the parameter that controls that. We also vary the number of simulations per step, which really just determines how many environment interactions the agent has at each step through the environment. And then we also vary the rollout policy. So we look at a random rollout policy where a random action is selected unless a ground station is accessible. and a heuristic rollout policy, which is just operating on a low dimensional safety MDP to guarantee that we're not wasting time finding where the resource constraint violations are. Instead, the agent can explore high value states with high reward. So here are the results from the heuristic rollout. I don't have the random rollout results in this presentation because they're quite bad, which is as we expected. But here you can see that fairly quickly on the right, we have average downlink utilization plotted. And at only 10 simulations per step and an exploration constant of 500, the agent reaches about 95% downlink utilization, which is our measure of optimality. At 100 simulations per step, the agent reaches about, I think, 97% downlink utilization. So it takes a long time to converge past that. So 10 simulations per step is actually what we use to generate training data. So after the generation of the training data, we did a large hyperparameter search on neural network architectures. So here we varied the activation function. We used leaky ReLU and TANH. And we also varied the number of nodes per hidden layer and the number of hidden layers. And we found that a leaky ReLU activation function gave us the best performance, around 4 to 6 hidden layers and 250 or 500 nodes. And hyperbolic tangent activation function performed kind of poorly just across the board. Another thing we did was we grabbed a specific leaky ReLU architecture at 250 nodes per layer, and we wanted to look at how some of the other parameters affected the performance. And what we found was that it's actually fairly robust to the other hyperparameters, like the dropout rate, which is just the probability that a node is randomly dropped during training, or alpha, which controls the slope of the activation function for x less than 0. Now, I should say alpha equals 0.5 is kind of a poor performer across the board, but the other hyperparameters are pretty robust. And in some cases, we actually exceed the performance of Monte Carlo tree search at 10 simulations per step. With only a single environment interaction. So generalizing training across a bunch of different initial conditions and using a neural network to regress over that in some cases can be more robust. We also wanted to examine the learned behavior and see what the variability in this learned behavior was across high-performing state action value networks. And what we found was that each agent spends about the same amount of time charging, meaning that it's kind of maxing out the amount of data it can put in the data buffer. But different agents spend different amounts of time trying to downlink. So some agents spend only 30% of the time downlinking and achieve 95% downlink utilization. Other agents spend 95% of the time doing this to achieve the same downlink utilization. So learned behavior varies greatly across the agents, and I think this speaks to the problem complexity a little bit. We could probably push it a little bit harder such that fewer networks perform well. The last thing we wanted to do was kind of determine what the optimality gap is and how MCTS and state action value networks compare to standard optimization techniques like genetic algorithms. So we put together a simple genetic algorithm, and we found that it appears that the optimal downlink utilization is right around 99.8%. So both heuristic MCTS and the value networks are within a couple percentage points of this. But what's most striking is that the value network can achieve almost near optimal performance in a fraction of the time after training. We're talking 5 orders of magnitude less time, which is a very good case for onboard execution. So conclusions of this work: Monte Carlo tree search computes near optimal planning solutions, and state action value networks can match or exceed the performance of MCTS with a 5 order of magnitude reduction in execution time after training. We also found that the complexity of the posed problem does not really merit the application of more complex algorithms like AlphaGo, which we initially wanted to implement. So in future work, we're going to increase the problem complexity by adding multi-target imaging to the scenario, where each target is its own action, and we're going to apply AlphaGo to solve this. And then we're also going to perform a study on how well these results extrapolate to orbital parameters outside of the training distributions, so we can make an even stronger case for generalizability. And that's all. So thank you for watching.